What if you could rewind time? Go back to that one moment you've always replayed in your head. It's the stuff of dreams, right? Well, what if I told you that the key to this ancient human fantasy isn't in a DeLorean, but hidden in the heart of the universe's most terrifying and mysterious monsters? Places where the rules of space and time break down, where logic itself surrenders to infinity. These are black holes. And today, we're going to discover how these cosmic beasts might not just be about destruction, but could be the ultimate gateway to understanding time itself. This isn't a blueprint for a time machine. This is a journey to the edge of reality to ask what time even is. So let's dive in. The birth of an idea, Einstein's nightmare. Our story starts in the early 20th century with a young man working in a patent office. His name was Albert Einstein. He proposed that time and space weren't absolute. Instead, they were woven together into a single, flexible fabric, space-time. Think of it like a giant, cosmic trampoline. Mass bends this fabric. The heavier the object, the deeper the dent it makes. Earth makes a small depression. The sun makes a deeper one. But Einstein's equations whispered about something far more extreme. If you crammed enough mass into a small enough point, the fabric of space-time could stretch so thin, it would essentially tear. This point of no return, this bottomless pit from which not even light could escape, would come to be known as a black hole. But here's the kicker: Einstein himself didn't really believe it. To him, it was a mathematical oddity, a ghost in the machine of his equations, too strange to be real. The idea of a singularity, a point of infinite density, went against his elegant view of the universe. But the math was stubborn. It didn't lie. The unlikely hero, the soldier who drew the border. Just a month after Einstein published his theory of general relativity, a young German astronomer named Karl Schwarzschild, fighting on the Russian front, read the paper. There, in the mud and horror of the trenches, perhaps seeking an escape, he played with the equations. And he found something incredible: the exact solution for the curvature of spacetime around a perfectly spherical mass. This solution defined the black hole's ultimate boundary, the event horizon. Think of it as the point of no return, like the edge of a waterfall. Once you go over the edge, there's no swimming back. Schwarzschild mailed this solution to Einstein from the front lines. Einstein was astonished. Tragically, Schwarzschild died shortly after from an illness contracted at the front, never living to see the monster he had discovered become a reality. Where time stands still, the ultimate thought experiment. So why does time go so crazy at the event horizon? Here's a mind bender to wrap your head around. Imagine you're an astronaut falling towards a black hole. I'm watching you from a safe space station. As you get closer to the event horizon, from your perspective, time feels normal. You check your watch, seconds tick by just fine. But from my point of view, you start to slow down. At first, it's subtle. Then, your movements look like you're moving through molasses. Finally, at the exact moment you reach the event horizon, to me, you freeze. Like a photograph. Your light reddens and fades away. You become a permanent monument on that horizon. But what do you experience? For you, time flows normally, and you might just fall straight through to whatever secrets lie inside. But for the rest of the universe, you never actually cross that line. This is one of the most stunning predictions of general relativity. Time is relative. A black hole warps the fabric of spacetime so severely that it puts the brakes on time itself, nearly stopping it. This makes it a theoretical machine for traveling into the future. If you could orbit a black hole very close to the event horizon for a few hours and then return to Earth, thousands, or even millions of years might have passed. You could, in theory, watch the pyramids be built and return to a world where humanity has spread across the stars. That is, if you could survive the trip. Culture and history's encounter with black holes. While the idea of black holes feels modern, humanity has been flirting with the concept for a long time. In the 18th century, the English astronomer John Michel and the French scientist Pierre-Simon Laplace conceived of dark stars, bodies so massive and dense that light couldn't escape. But that was based on Newton's physics. It lacked the profound depth of Einstein's vision. But what about older cultures? The Aboriginal Australian concept of dreamtime describes a timeless dimension of creation. Some ancient Hindu texts describe the universe expanding and contracting with the breath of a giant being. Doesn't that contraction sound familiar? And here's a little-known, fascinating story for you. In the 1970s, miners digging a shaft in South Africa's Witwatersrand Basin, one of the largest gold deposits on Earth, started finding strange, incredibly dense, spherical metallic objects. They were called the Klerksdorp spheres. Science says they are likely natural formations of pyrite. But here's the cool part. This region is rich in iridium and osmium, elements that were likely deposited by a supernova explosion billions of years ago. So, these spheres might be a tangible piece of a star's death, perhaps even the birth of a black hole, right here on Earth. They could be evidence of the universe's most violent events, lying at our feet without us even knowing it. The quantum revolt, Hawking radiation, and the information paradox. For a long time, we thought black holes were truly black, that they emitted nothing. That is, until Stephen Hawking came along. Hawking applied quantum mechanics to the edge of a black hole, and everything changed. Quantum theory says that empty space isn't really empty. It's a bubbling sea of virtual particle pairs, constantly popping into existence and annihilating each other. Hawking realized that if this happened right at the event horizon, one particle could fall in while the other escaped. This escaping particle is seen as a loss of energy, meaning the black hole very, very slowly evaporates. This is called Hawking radiation. It was a monumental discovery, but it created a terrifying paradox, the information paradox. When something falls into a black hole, what happens to all the information it contained? According to Hawking's initial idea, that information would be lost forever when the black hole evaporated. But that violates a fundamental rule of quantum mechanics. Information cannot be destroyed. This paradox has split physicists for decades. Hawking once insisted information was lost, even making a famous bet about it. Then, he changed his mind. It was a huge deal in the science world. The solution to this paradox might hold the key to understanding time. Some theories suggest information might be stored on the event horizon like a hologram. Just like a 2D credit card strip holds all the information for a 3D object. This holographic principle is so profound that it suggests our entire universe might be a holographic projection. Think about that for a second. The flow of time itself might be an illusion generated by this cosmic code. Photographing the invisible, the first image, and the future. All these theories were thrilling, but there was a problem: we couldn't see them. Until April 10, 2019. The Event Horizon Telescope collaboration, a planet-sized virtual telescope made by linking 8 radio observatories across the globe, made a historic announcement. They had taken a picture. The first ever image of the supermassive black hole at the heart of the galaxy M87. That glowing orange ring of fire? That's the light from superheated gas swirling around the event horizon, unable to escape. Its shadow matched the predictions of Einstein's equations perfectly. This wasn't just a picture, it was a testament to human ingenuity, a victory of our species peering into the face of the ultimate cosmic monster. And the future? Observatories like LIGO and Virgo are already hearing the ripples in space-time caused by black holes colliding. We're not just seeing the universe anymore, we're listening to it. The secret in the heart of time. So, are black holes the ultimate time machines? The answer is yes and no. They are undoubtedly incredible tools that warp time and offer us a laboratory to understand its nature. But they also give us far more questions than answers. The information paradox, quantum gravity, the holographic principle, these are the frontiers of the battle for physics' ultimate theory. Perhaps the greatest lesson black holes teach us is this: time isn't the simple, steady tick-tock we measure on our wrists. It's a dynamic, living fabric, woven together with space, warped by mass, and nearly brought to a standstill under the most extreme conditions. Trying to understand them is really an attempt to understand our own existence. As the poet might say, yesterday is today's memory, and tomorrow is today's dream. Black holes, by twisting and tangling those memories and dreams, show us how fragile, and yet how magnificent, time really is. They may not be the universe's ultimate time machines, but they are, without a doubt, its ultimate teachers. Thank you for joining us on this journey. Remember, the next great discovery might just be made by you, right there on the other side of this screen.